Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 7, Differential Equations. Today's topic is 7.2, where we're verifying solutions with differential equations. Enjoy today's notes. All right, welcome to 7.2, Verifying Solutions of Differential Equations. Jumping right in, derivatives can be used to verify that a function is a solution to a given differential equation. Now, we already covered some of this back in lesson 6.8, where we found these things that are called particular solutions. Let's remind ourselves of what we did. One of the key things that we would want to emphasize thinking about, the differences between what's called a general solution or a particular solution is we know that back when we were taking antiderivatives in chapter 7, a general solution, we knew it was a general solution because when we took that antiderivative, it had a plus c on the end. And that c represented a constant that the function could have. And it's general because, an antiderivative could have any type of constant in that place. And so this is just saying, hey, this is going to stand in for all of them. What we then did is we said, okay, well, if we have a little bit more information about the function itself, we can find what's called the particular solution, which is where we can find the specific c values. So we're finding out what c is. And so this is sort of the key difference between the two of those. A general solution is just where we have a plus c, and we're not really worrying about what the c is, or we don't have enough information for it. And a particular solution is where we find out what that specific c is, and we really lock in into what the specific function is for these problems. Let's see this here in number 1. So we're saying if dy dx is equal to e to the 2x minus 2x squared, find the particular solution of y if we know that y of 0 is equal to 4. So first off, they're asking us to find that particular solution, so we're going to find out what that c is. But the thing that allows us to do that here is that they're giving us this starting point. We know that for the y function, if you plug in x equals 0, that you're going to get an output of 4. So what we're going to do here to find out what this is we're going to say, all right, well, if dy dx is this e to the 2x minus 2x squared, if we take the integral of each side, then y is going to be the integral of e to the 2x minus 2x squared dx. All right, throw back to chapter 6. We're going to need to take the antiderivative of the right side of this equation if we're going to find it. Here, if we think about this e to the 2x function, because it's an e to the x function, we know both the derivative and the antiderivative would be itself, but this has an inside, right? It has like a raised to the 2x power. And if we took the derivative, we would end up multiplying by the derivative of 2x, which is 2. But if we take the antiderivative, we're going to do essentially the opposite of that. So instead of multiplying by 2, we're going to actually end up dividing by 2. And we're going to say this is e to the 2x, right? It stays the same, but we're going to divide by that derivative of 2x, which is 2 here. Next, what we're going to do is we're going to move on to this negative 2x squared part. Here we can just use our power rule, where if we're doing an antiderivative, we add 1 to that exponent. So that's going to make it a 3. And then we need to divide by what that new exponent is. So I have negative 2x to the third power, and I need to divide by that new power, divide by that 3 here for this. And here, because we're taking this antiderivative and we don't have limits of integration, we're going to end up with a plus c on the end for that. Now, at this point, we have enough information here to now use our initial value to plug in and find out what c is. So we're going to move into that. We know that when we plug in x is 0, which we can plug in for both of these two pieces, that the output, the y value, is going to be 4. So I'm going to substitute that in. We're going to say 4 is our y, and that's equal to e to the 2 times 0 over 2. Minus 2 to the 2 times x, not 2 times x, so 2 times 0 to the third over 3, plus whatever c is. On the left side, we have 4 is equal to 2 to the 0 power. Anything to the 0 power is 1, so that's 1, and we're still dividing by 2, so that's 1/2. And then here, if we have 0 to the third, that's 0. 2 times 0 is 0. 0 divided by 3 is still 0. So this term is going to go away, and we're going to be left with a plus c. That means if I want to get that c by itself, we need to subtract 1/2 on both sides. So 4 minus 1/2 is going to tell me here that 3.5 is equal to my c value. So if we want to find our final answer for this, or write our final answer, we want to write this particular solution. We're going to go back to our general form that we had here, our general solution, and we're going to just plug in that c value that we found. So my final answer for this is going to be y is equal to e to the 2x over 2 minus 2x cubed over 3 plus our c value, which was 3.5. This would be my final answer for problem number 1. And that is, again, what we're talking about here is they gave us a differential equation. We're trying to find the particular solution. So what is the y equation that has this derivative but also goes through this point? And this is the only one that can be. So e to the 2x over 2 minus 2x cubed over 3 plus 3.5. Number 2, this problem is exactly the same. A curve has a slope of e to the 2x minus 2x squared at each point xy on the curve. What is an equation for the curve if it passes through the point 0, 4? So again, this problem is exactly the same as number 1. This is just worded in a different way. What we're trying to do here is we're trying to point out common different ways that sometimes this shows up on the AP exam. Sometimes they might be really straightforward and say, hey, here's dy dx. Hey, here we know that y of 0 is equal to 4. Otherwise, it might be in some context. They might say, hey, the curve has a slope of this. So if it has a slope, we know that that's the derivative, right? So that's telling us this is the derivative function, but notice, hey, they didn't say that this was dy dx. We need to know that slope means derivative. And they're saying, what's an equation for this curve if it passes through the point 0, 4? So instead of them saying, hey, y of 0 is 4, they actually just said, hey, it goes through the point 0, 4. So this is the same thing, just written in a different context. We should be familiar with both of these types of ways, because depending upon the problem, it might be in one way or the other, but the work for this would be exactly the same. I'm not going to do it over again. It is exactly what we would see in problem number 1. All right, number 3, we're going to jump into what I'm going to explicitly say. This is a hard example, and I think the idea here is we're trying to see like a harder version of this type of problem. And I'm going to say that up front. I would expect most of our practice problems are going to be, easier than this, but we want to make sure that if you got a challenging one that you know what to do. Let's see what they say. So if d squared y over dx squared, so the second derivative, is equal to 1 over x squared plus 1 minus 2x quantity squared, find the particular solution of y if we know that y prime of 1 is equal to 7 over 6 and y of 1 is equal to 0. Now, one of the things that's going to be challenging about this problem is we're trying to find the particular solution of y. We want to find out what the equation of y is, but they gave us a second derivative here, which means I'm going to have to take 2 antiderivatives, right? I'm going to have to take an antiderivative to get to y prime, the first derivative, and I'm going to have to take another antiderivative to get back to y. And so really the challenging part for this problem is just the length of it. There's a lot to it. In fact, I'm going to make sure that I'm writing small for this because we're going to need some space to get through all the steps for it. All right, so how do we start this one off? Well, we know the second derivative of this function is 1 over x squared plus this 1 minus 2x quantity squared. So if we take the antiderivative of it, that's going to give us dy over dx, so the first derivative, is going to be equal to the integral, or that antiderivative, of 1 over x squared, which we could write as x to the negative 2, plus that 1 minus 2x squared dx. Now, the first part of this, we could just use our regular power rule, right? From thinking back to chapter 6, we can add 1 to that exponent and divide by that new exponent. So dy over dx is going to be equal to x to the negative 1 over negative 1. And then here, if we think about this 1 minus 2x quantity squared, what we could do is I'm going to actually change up my color here. I'm going to treat this part of it as if it were u substitution. So we're taking the integral of just this part that's right here. If we think back to chapter 6, the way that we could do our u substitution, so we could say, hey, the inside part here is 1 minus 2x. So u is equal to 1 minus 2x. And if we take the derivative of that with respect to x, that would be equal to negative 2. So if we multiply dx to the other side, we get negative 2 dx. And that means that dx is equal to du over negative 2 for that. So if we substitute in for this, we get plus our, I'm going to leave this still as an integral because we haven't taken the antiderivative yet for that part. But it's going to be plus u squared, right? Because that 1 minus 2x is our u. And then that dx is going to become du over negative 2 for that. That negative 2, because it's in the denominator, is like a negative 1/2. We can bring that on the outside and then take the antiderivative of this u squared part. We know that by the power rule, we're going to add 1 to that exponent and then divide by the new exponent. So we're going to end up with an exponent of 3, and we're going to end up with a divided by 3 for that. We also know that we would need to substitute back in for u. So ultimately, when we do that, we're going to end up with dy over dx is equal to that x to the negative 1 over negative 1 plus negative 1/2. Again, that's coming from this this constant here. We've essentially got a 1 over negative 2. That's the same thing as negative 1/2. And then the antiderivative of this is going to be equal to 1 minus 2x to the third. That's our u to the third divided by 3. And then we've got our plus c here for this. So what we can do is we can simplify. We can say, all right, this is dy over dx is equal to, if we were to simplify this x, because it's a negative exponent, would need to go to the denominator. So this is the same thing as negative 1 over x plus, we've got a negative of this numerator. If we multiply, negative 1 minus 2x cubed over 2 times 3, which is 6, plus our c. At this point, what we're going to need to do is we're going to say, okay, well, they gave me some information here. They said that y prime, aka that first derivative, or dy dx, if we plug in x equals 1, then we get 7 over 6. So we need to find this c value. And so what I'm going to do is I'm going to move up here, and we're going to continue for this, trying to find the particular solution for the first derivative. So dy dx is going to be 7 over 6. Again, I'm using this information right here in order to plug in into my equation here. 7 over 6 is going to be equal to negative 1 over our x, which is 1, plus negative 1 minus 2 times 1 cubed over 6 plus whatever c is. And so if we want to simplify that we get 7 over 6 is equal to negative 1 over 1, which is negative 1, plus, what's this going to be? We've got 1 minus 2, so that's negative 1 cubed. Negative 1 cubed is going to be negative 1, so we have a negative 1, which gives us a positive 1, divided by 6. So plus 1 over 6 plus our c. If we wanted to simplify some more, what we could do is we could subtract 1 over 6 from both sides. So that's going to give us 7 over 6 minus 1 over 6 is 6 over 6, or just 1. And that's equal to negative 1 plus c. So if we add that 1 to both sides, we get that c is equal to 2 for that. So our equation then for y prime, or dy dx, is going to be equal to, looks like we've got negative 1 over x plus negative 1 minus 2x cubed over 6 plus 2. And that would be our dy dx. Now here's the thing that makes this tough. This is essentially where we would stop if they were just asking us to find the first antiderivative for this, but they want us to find what y is. And we've just found out what dy dx is, which means we need to go through this process one more time in order to do that. And so in this case, I'm I'm going to just highlight this because this is sort of like the halfway point, and we have definitively found out what dy dx is. What I'm going to do, I think, space-wise, is I'm going to jump down here. So I'm going to end up erasing this part here just as an FYI. Maybe if you need a separate sheet of paper or something like that, that might be helpful here for number 3, just because it's a longer one. But continuing this work for this, we know that if we've got dy dx, that if we want to find y, we need to take the antiderivative. And so what we can say is that antiderivative y is going to equal the integral of negative 1 over x plus this negative 1 minus 2x quantity cubed over 6 plus our 2 dx. And so if we want to do that, we can take the antiderivative of each of these parts. What's going to happen if we do that is, well, this is like 1 over x, which is one of our special antiderivatives from chapter 6. 1 over x, that antiderivative is the natural log, and because it's negative, it's going to be a negative natural log of the absolute value of x. And we've then need to take the antiderivative of this part, where we noticed sort of in the last problem we did use substitution in order to do this. We ended up multiplying, or rather adding 1 to the exponent to get us, in this case, we'd have a 4. And we need to divide by that new thing, so we'd be dividing by 4 as well. And then we also end up dividing by a negative 2 because of that substitution of the du over negative 2 is dx. What this ends up being, if we do that use substitution, is we're going to end up with, in this case, actually a positive 1 minus 2x to the 4th power over what ends up being 48. And again, where does this 48 come from? It comes from the 6 that was there times the 4, which is 24, times the 2 from that use substitution to give us our 48. So that's where this is coming from. This plus 2 at the end, if we take that antiderivative, it's going to become 2x. And then, of course, we have a plus c because we took that an antiderivative. From there, we are at a point again where we need to find out the c value. Going back to original problem, they're telling us here that y of 1 is equal to 0. So we know that when x is 1, y is 0. So I'm going to substitute that in. We're going to say 0 is equal to negative natural log of 1 plus 1 minus 2 times 1 to the 4th over 48 plus 2 times 1 plus whatever c is. So 0 is equal to natural log of 1 is going to be 0, so this is negative 0, just goes away. Here we've got 1 minus 2, so that's negative 1 to the 4th. Negative 1 to the 4th is positive 1, so this is going to be 1 over 48. And then we've got plus 2 over 1, so that's plus 2, plus whatever the c value is. And so if we're trying to get c by itself, what we could do is we could subtract 2 from both sides. We could subtract that 1 over 48 from both sides. 2 we can treat as like 96 over 48. So negative 96 over 48, that's the same thing as negative 2. And that's going to be equal to 1 over 48 plus c. So then we can subtract that 1 over 48 from both sides. That tells me that c is going to equal negative 97 over 48. So we've got our c value. What does our final answer for this problem look like? Whew, this looks like quite a bit of work. Y is going to be equal to negative natural log of the absolute value of x plus 1 minus 2x to the 4th over 48 plus 2x. And then we've got our c, I'm just put a minus 97 over 48 for that. So this is our final answer for this problem. Again, this is above and beyond of the level of a majority of these problems. This is definitely hard mode for this, but we wanted to give a good example of what this would look like. We're going to need to do it twice. But again, this is not something I'd say is frequent on like quizzes, tests, or even the level of the AP exam, but still useful that we can do that as well. I'm going to pause here just for a moment in case you need to pause the video or to take a screenshot of this, because again, I'm going to be erasing this work down here so that we can continue and finish up problem number 4 here. So let's pause. All right, going back to our notes, we're going to go to the recall. So recall here some things from chapter 6. We want to remember some things about the derivatives and antiderivatives of sines and cosines and things like that. We talked back in chapter 6 about this sort of circle, so I'm going to show it sort of over here. We know that if you've got sine of x, that if you want to get the derivative of sine of x, that becomes cosine of x. And we know from chapter 2 again that if we take the derivative of cosine of x, that we get negative sine of x. If we take the derivative of that, we're going to get negative cosine of x. And if we take the derivative of that, we end up back at sine of x again. So essentially we can go clockwise around this circle as many times as we need to find, hey, which derivative am I at, or what am I going to get for this? We also learned in chapter 6 that we can go the opposite direction if we're doing an integral, right? If we're taking an antiderivative. So I'll just say that we can go counterclockwise on this with those little integral symbols here to show that we can go the opposite direction to find what those derivatives are. So using that information here, just recall some information. We know that the derivative of sine, if we're thinking about, okay, we've got sine, the derivative is going to be cosine of x. So that is equal to cosine of x. We also know that the derivative of cosine, if we're at cosine, that derivative is negative sine of x. Again, these are derivative rules from back in chapter 2. Definitely useful to know for the AP exam. But if we take the integral, aka the antiderivative of sine, we're going to go the opposite direction. That's going to give us negative cosine of x. So that is negative cosine of x. And because there's no limits of integration here, we don't want to forget our plus c. Similarly, if I take the integral of cosine of x, I'm going to be moving to positive sine of x. If I take that antiderivative, so that is going to be positive sine of x plus c. Again, because we have no limits of integration for that integral. So that's just some useful information to know. And it's going to be useful here for problem number 4 as we move into this last problem for today. So problem number 4, one common thing that comes up on the AP exam is they'll give you an equation like this, where it says, okay, y is equal to k times e to the negative 4x minus 2 times sine of 5x. And they're saying what value of k needs to be do you need to have for that to be a solution to this differential equation? Y double prime plus 25y is equal to negative 82 e to the negative 4x. So what we'll notice here, first off, is they're giving us this differential equation where they're saying that the second derivative plus 25 times our y, this equation here, needs to equal something. So if I'm going to verify the solution, right, the title of these notes is verifying the solutions, what I need to do is I need to plug both the second derivative in and our y equation in to this equation to help me find out what the k value needs to be. So the first thing that I'm going to do is I'm going to take the first derivative of this equation. So if y is this, the derivative of that, y prime, is going to be, well, the derivative of k times e to the negative 4x, because it's got that negative 4x, we're going to essentially do the chain rule here. That's going to be negative 4k e to the negative 4x, right? That derivative of the inside is negative 4, so it gets multiplied by that term. The e to the x part stays itself because the derivative of e to the x is itself. Next, if we take the derivative of negative 2 sine of 5x, that 5x is an inside, and the derivative of that is 5. So that's going to multiply to the outside here to give me a negative 2 times 5, or 10, cosine of 5x, because we know the derivative of sine is cosine. And so that is going to be our derivative equation for y. So that's y prime. But we need y double prime. So we're going to take the derivative again. We're going to say y double prime is equal to the derivative of this part, which again, because this negative 4x is inside of the exponent, we do the chain rule. Negative 4 is going to get brought outside, multiplying with this negative 4 to give us a positive 16, k e to the negative 4x. And then again, similarly, this inside of 5x, the derivative of that is 5, so that's going to get multiplied out here. The derivative of that negative cosine is going to become a positive sign, so that's a positive 10 times 5, which is 50, sine of 5x, if we take that derivative. So this would be our second derivative. What I'm going to do is, we know that we're going to need to plug in y double prime, and we're going to plug in y into this equation. We know that y they gave us, so that is going to go there in this spot. Our y double prime is going to be this equation here that's going to go in for that spot. So I'm going to substitute both of those in for this equation. And let me just change my color that I'm using here. Y double prime, we just said, was 16k e to the negative 4x plus 50 sine of 5x. So that's our y double prime, which I'll just show again. We just substituted that in for our y double prime. And they're saying next it's plus 25, so plus 25 times y, and y is this equation that they gave us here. So that is k e to the negative 4x minus 2 sine of 5x. And I'll highlight that here in yellow, what we just substituted in. And they're saying that that's going to equal negative 82 e to the negative 4x. So that equals negative 82 e to the negative 4x. So again, each of these pieces is coming from this equation. All we just did was substitute y double prime in that we found here for that, and y in for this. So at this point, my hope is we're going to try to now find out what k is. We've substituted everything in. We've got a couple of different k's. It looks like I'm seeing one here. I'm seeing one over here. Let's expand and try to simplify and just sort of see what happens here. I'm going to start here with this 25, which needs to be distributed to both of these things. If we do that, I'm going to rewrite this whole row, 16k e to the negative 4x plus 50 sine of 5x. And then if we distribute that to both of these, we've got plus 25k e to the negative 4x minus 50 sine of 5x. Again, that minus 50 is coming from that 25 times that negative 2 to give us that. And that's still equal to the right side, negative 82 e to the negative 4x. Well, the nice thing here is, notice we've got a 50 sine of 5x and a negative 50 sine of 5x. Those are going to cancel each other out. So those are going to cancel, which is going to make that a little bit easier for us to work with. Additionally, we've got 16k e to the negative 4x and 25k e to the negative 4x. They both have this k e to the negative 4x, which means they're like terms. I can combine them. 16 plus that 25 is going to give me 41 k e to the negative 4x. And on the right side, that is still negative 82 e to the negative 4x. What I can do on both sides is actually divide by e to the negative 4x. So those would cancel each other out because they're the same, which means that 41k has to equal negative 82. If we divide by 41 on both sides, we get that k is equal to negative 82 over 41, which is actually just negative 2 for this problem. So k being negative 2 is the only thing that k could be that would make this differential equation true. And again, process, because we saw that it had a y double prime, we took the first derivative and then the second derivative, and then substituted in for that equation, simplified, and then we were able to solve for our k value here. But that's it for problem number 4. The rest of today is going to be working through the practice problems that we've got here on the rest of our sheet. Good luck on those. Check your answers, and definitely please reach out if you have any questions. Have a great rest of your day.